This is 6.2.5.3. We're interested to continue to study the use of frequency response equation to find out the response, or especially the steady state response given a particular input. We're now given an input 1 and 1 cosine 0.1 pi n. And this is a difference equation, was derived in the previous page, and we saw that the transfer function, or sorry, the frequency response is exactly this equation over here. Now, as the name implies, the frequency response tells us how the frequency will behave at different frequencies. So the frequencies is exactly here. We'll substitute different omega for the frequency that we are interested in to calculate h of omega, and we'll find the amplitude as well as the phase of this value and use them. Given that we have xn as this, then the frequency of 1 is simply, actually what is 1? It is actually 1 cosine 0 pi n. You can think of it this way. The frequency is 0 because 0 pi n is simply 0. So cosine of 0 is 1 all the way for all n. So a DC term of 1 is simply a 0 frequency, omega equals to 0. What about 1 cosine 0.1 pi? So this is the omega for this cosine. Omega is 0.1 pi. So we are interested in two different frequencies. We'll substitute omega equals to 0 for the transfer function. So we are substituting simply omega equals to 0 here. And this is a complex number dividing by a complex number minus by a real number. Outcomes in this example is actually 2 plus j0, a real number. So it shows you that at this particular frequency, the amplitude will be changed by multiplying by 2 with phase of 0. What about 0.1 pi? So you substitute 0.1 pi into the frequency response. So and then you will get a real and complex number. This is not good for us. We prefer not the rectangular representation, we prefer the polar representation. This is the magnitude and this is the phase. So how do we use that? Well, let's see what we do. The input 1, which is at frequency 0, is multiplied by 2, the amplitude. So yn equals to 2. The cosine at 0.1 pi, the original amplitude is 1, is multiplied by 1.829. So this is the new amplitude. This is still cosine 0.1 pi n, and the new phase is minus 0.2865, which is here. So what did we just do? Again, what we did was that we take the yn to generate the frequency response. We identify the inputs frequency to calculate the frequency response at different omega, and we use this to change the input by scaling the amplitude and phase. So this is the amplitude being scaled, this is the phase. Here 2 has no phase, so that's why the output is 2. This is actually the steady state response. So you notice that there's no transient here. There's no E minus AT or whatever. This is a steady state response. So the frequency response allows us to change the input to the output and only express the steady state response. This is a very typical questions that we'll set for the quiz and exam. Thank you. Right, but before I end, I will show you what is my input and output using MATLAB. The input is the blue dot, which is unit step 1, and then the green is the steady state response. So the blue is 1 multiplied by 2, which is a gain. So this is the steady state response. What about the red dots? The red dots is generated by the difference equation, and you will see that it takes about maybe about 6-7 samples before it becomes steady states. This is the transient response that is not captured if we have studied the problem using the frequency response approach. So to get the steady state response, either you write the difference equation and generate the simulation, or use Z transform. What about the cosine? So again, 1 cosine 0.1 pi is the blue. Can you see the blue here? Which is amplitude 1. There's no phase shift. So the maximum point is at n equals to 0. What about the green? The green is a phase shifted version of the blue, and with the gain of 1.829, and you will see that the green is a cosine, and this is a steady state response. There is no transient, but to get the transient we use the difference equation, which is the red dots, and you see that in the first 3 or 4 points it doesn't match with the green because it is still being in the transient state. And after the transient state has decayed away, the red line, the red dots generated by the difference equation becomes the green line. So the idea is that when we are using the frequency response, we are only getting the steady state response. Alright, let's see how we do it. The MATLAB code is here. So the idea is I tested and draw 2 different cosine. The first one is for 0 pi for the DC term. The second one is for 0.1 pi for the cosine. And basically I calculated the gain at the different frequency and the phase as well. And then I use this for loop to generate my input. So cosine, actually when omega equals to 0 is the straight line DC, and 0.1 pi for the second experiment. The yn is simply xn plus 0.5 times yn minus 1. So this loop is to generate the difference equation, and this reference equation is using the reference gain calculated using the frequency response. See, absolute of h from this frequency response, reference of phase from this angle of h, and we're computing the theoretical gain and phase shift, and then after that we plot. So maybe by studying this MATLAB code, you will now clearly know the difference between the steady state response and the transient response, and how we can get the 2 output. Thank you.